Hello, hello. Thank you all for coming. This is great. Happy to be back at another sub0. It's been several years now. I still remember the first one back in 2018, and it's always good to meet people who choose to spend quite a significant amount of time and energy building on code that we've put out into the world. And thank you all for coming. Today I'm going to talk about a new piece of code, something called Nomt, and how we're going to use it to potentially scale blockchains much further than was previously thought possible without reverting to, say, running nodes with a lot of RAM. So Nomt is a state database, and a state database is a critical component of a blockchain node. It's what stores all of the addresses and accounts and contract code and token balances and various pieces of data that smart contracts themselves keep. It's what makes a blockchain tick, right? Every node keeps its copy of this state database. It has its own copy of the state, and it has its consensus protocols and stuff to keep that in sync with other nodes. This is just the database. Our focus is on very high throughput commits or updates to it, really low latency lookups for contract and transaction execution, optimizing for Merkleized state, which I'll go into later, and very particularly optimized for modern solid-state drives, which are a form of storage commonly used, gaining in a lot of popularity, and they have certain characteristics, the modern hardware, and certain trends that we'd like to tap into. And we're also optimizing for full block state proofs. So, how do you generate, when you create a block, how do you generate a proof of every single piece of data touched within the execution of that block actually being part of the state at that moment? That's really important for coprocessors and cores, ZK proving, any kind of situation where you need to prove that a block execution was valid. You need these state proofs, and that's a key part of Nomt. It's a drag and drop replacement to an extent of RocksDB, MDBX, LMDB, LevelDB, which are all widely used in blockchain nodes. Now, these are general purpose databases, and they're built by very serious people. RocksDB comes out of Facebook. It's a fork of LevelDB that came out of Google. These are hardcore database engineers, and it's very hard to beat the performance of something like that. But we have a specialized use case, which enables us to do it. And the special feature of Nomt is that it encapsulates all of the state Merkleization within it. So instead of having a database where you then put Merkle nodes into it, we have a specialized store that keeps all of the Merkle tree data that, in a format that's really, really friendly to our use cases. It's inspired by this blog post, which was put out by Sovereign Labs, Preston Evans, CTO of Sovereign Labs. I'd say we've gone a little bit beyond what this blog post describes at this point, but it was a huge inspiration and really got our gears spinning on the potential of tapping into capabilities of modern SSDs, and we do use a lot of the techniques outlined in this blog post. The development of Nomt is funded with a grant from Sovereign Labs. They want to use it in the next version of their SDK. But we want Nomt to power blockchain throughput everywhere, right? I think that this is something, as such a central component to nodes, it should be used. Ideally, I'd like to see it used in Substrate. I'd like to see it in Ethereum nodes. I'd like to see it in every SDK that gets built, because frankly, it's just going to be better than the databases that are already being used in these nodes. If you want to see our code, and I'll put this QR code up again later, you can scan this QR or navigate to that URL. And I'll pause here for a couple seconds in case anyone wants to do that. All right, okay. Here are the people who built it. We're actually all here at the conference. We're three Rust systems programmers by trade from the Polkadot sphere. So that's me, Robert. On the left is Sergey Pepyakin. I've worked with him on we were part of the team that built Parachain's consensus from the years, say, 2019 to 2022. He worked on WebAssembly stuff. We've worked together for a very long time. Gabriella is around here as well. He's a graduate of the Polkadot Blockchain Academy a couple years ago. Why are we doing this? There's an underlying thesis. Large state versus fast transactions, large state versus high throughput. I think that large state is more important than really fast throughput. I think that if you can have a really large state with, say, dozens of billions, or in the future maybe trillions of state items all in a single node, that means more users, bigger network effects, better apps. Large state means state's cheap, more complex applications, more value add, better apps. But throughput, I'd say you need around 10,000 transactions per second to get 100 million daily active users. That's around 850 million transactions a day. So you need a few tens of thousands of transactions per second, but you don't really need 100,000 or 200,000. I mean, even with the broadest visions of what blockchain tech is going to be used for right now, I think 100 million daily active users is pretty good, especially as those use cases like payments and so on get tapped. I think we're going to do better than that, but as a benchmark, I think a lot of blockchain apps are still looking for their first 100,000 or million users. SSDs are getting better way fast. And I think the trend of the industry to outsource scaling to require nodes to have a ton of RAM, say a terabyte, 2 terabytes, 4 terabytes of RAM, is misguided long term because it doesn't make this state size versus throughput trade-off correctly. Also, it's really cool. For the too long didn't watch, here's like the key points. We want to support billions of counts on a 4 terabyte SSD. Consumer hardware, not that expensive, costs a couple $100. We want to target 25,000 worst case transactions per second. That's simple transfers. Random account A transfers to random account B for V1, and that's against a state with 1 billion accounts. That's our target for V1. Benchmarks are good so far, but you'll see the numbers when it releases. And potential for cheap and kind of free scaling, a little bit like the Solana hypothesis that we'll just get better with hardware because SSDs are getting better very quickly. And Nomt databases are fully authenticated, which makes them ready for interoperability. You can't bridge out of Solana because they don't have a Merkle tree. You can bridge out of a chain that uses Nomt because they have a Merkle tree. Very crucial. What's a state database? Just a key value store, stores keys that maps to values, address to balance, contract address to code, state items, stores tokens, anything you can really think of. If you're at a pallet in Substrate, you define your storage every day when you're writing that. That's all kept in this state database. Let's talk about authenticated state trees. So this is a class of algorithms, and it includes stuff like Merkle trees, also includes Verkle trees, all the new stuff with KZG commitments. It doesn't have to be a Merkle thing, but I call them authenticated state trees. The goal of an authenticated state tree is to encode the entire state of the blockchain, and you have a super light commitment to that entire state and everything contained within it, we refer to as the state root. In most blockchains, other than, say, Bitcoin and Solana, this state root appears in every block, right? Like if you look at a Substrate or Ethereum block, there's a state root within it, and that commits to all of the state data at that point. And you can use that to prove the value of any item in the state at that point. So it's really useful for light clients. Now, in practice, most users aren't running a light client on their phone. They're not getting Merkle proofs or remote RPC, because frankly, people don't seem to care about that. You can use it for that. The big one is that it's incredibly important for interoperability because blockchain bridges are built on light clients. And that's where you can't forego these kinds of authenticated data structures. We use a binary Merkle tree. It's simpler than the Merkle-Patricia tree of Ethereum and the modified version that's used in all the Polkadot chains. It's very simple construction. It uses 3 kinds of nodes. You have branches, which have 2 nodes below them. You have terminators, which are just nodes that contain nothing. And then you have leaves, which encode a key value pair. The way that you look up something in this tree is like, let's say I wanted to look up key like 1001. First I'd go right, that's 1. The next one is 0, so I go left. Next bit is 0, so I go left. And then I find a leaf. And the leaf essentially stands in for there is only one thing beyond this point. And that data is stored, what the full key is and what the value is stored within that leaf node. Super simple construction. Now, what this is meant for is very high entropy keys. So keys that are basically just hashes. There are some tweaks that you can make to this that are, make it useful for variable length keys, which are very useful from an application perspective and something that people who are familiar with Polkadot SDK palettes use every day. We know how to make those modifications, but it doesn't really impact the rest of the architecture. But let's take a detour, talk about SSDs, why they're so important, and what's happening with them. So typical high-end SSD has the following specifications at this moment. It's going to cost maybe $300, $400. We're not talking about very top of the line here, although I think we could. But let's say like $400 for high-end, $600 for top of the line. 4 terabyte capacity. That's a lot of capacity, and it's a 40 microsecond latency. So you make a request, you get an answer in 40 microseconds, and it can do 1 million IOPS, so IOs per second. And the interesting thing to note here is that these are random IOPS. This is reading anywhere or writing anywhere on the disk. If you compare that to a hard drive, you actually have to spin the drive until it comes around to the place that you're reading. And then you do another random lookup in it, you spin the drive again. Super slow. SSDs are not like that, so they're very good at random access, reads and writes. Breakdown of latency. You send a request to your SSD, wait 40 microseconds, and then comes back. The longer your queue is, the longer the latency gets. Throughput. You want to send a bunch of requests and get back answers, not necessarily in order. SSDs can handle that, say 1 million of those a second. That's a lot. What's an I/O? It's a 4 kilobyte single page read or write operation on the disk. So SSDs always work in increments of exactly 4 kilobytes. If you try to read a single byte, it's going to read 4 kilobytes that contain the byte you care about. Try to write a single byte, it's going to do exactly the same for the write. So you want to structure things when you're working with SSDs to pack as much useful data into that 4 kilobyte unit of a page as possible. That's how you write an SSD-aware database. SSDs are advancing very rapidly in cost. This chart projects that SSDs are actually going to be cheaper per terabyte of storage than hard drives are, according to the current learning rate of the technologies, by the year 2030. We'll see, but it's definitely getting better and fast. Here's a comparison between a top-of-the-line SSD from February 2024 versus a top-of-the-line SSD from September 2020. So in 4 years, we've gotten 500 million more IOPS, so 50% increase in IOPS. The price at launch is comparable. It's expensive, but it's really not breaking the bank for a serious production system. As you can see in the 2020 example, and just in the space of, say, 9 months, the prices for even these models are coming down rapidly, and the capacity is also increasing. I wouldn't be surprised to see 8 terabyte drives with 2 million IOPS in a couple of years. It seems reasonable. SSDs are also getting better controllers. Here's another headline that shows, just from a few months ago, here's an SSD controller that can do 2.5 million IOPS on the new PCI Gen 5 connection. So the general story I'm saying here is SSDs are getting really good really fast, and writing code that takes advantage of SSDs is probably going to get a free ride on the improvement of SSDs over time. All of these things are possible. You can have 25,000 transactions per second. You can have a full node whose hardware costs less than $1,500. You can support billions of counts, and you can have interoperability. You can have all these things. You don't have to sacrifice them. You don't. But why not just add more RAM? I mean, we've seen certain projects turn around and say, hey, disk is really slow. We're waiting on the disk all the time for our block execution, transaction execution. Why don't we just put the whole state into RAM? Well, if you actually drill down into what it means to have a machine that has terabytes of RAM, actually the most RAM that you can really put in a server right now is 12 terabytes. And it's going to cost you like $40,000. Way out of reach for anyone who's not like doing this for a living and has some funding to deal with. And that's DDR4 RAM. It's not DDR5 RAM, which is already a couple of years old at this point. If you wanted to just do 4 terabytes of RAM, so to say the same as an SSD of comparable size, it costs $5,000 US. 4 terabyte SSD is like 400. SSD reads could even be faster than copying data in RAM due to direct memory access, because SSDs just copy the data right into your RAM, so they don't need to go through the CPU. That means if, future direction, if you have a few SSDs, you might actually be able to get data off the SSDs faster than you could load it from RAM, copy it with the CPU into another location, and then work on it. Just a thought. And PCI, which is the technology that SSDs use to communicate with the rest of the components on the motherboard, getting very, very crazy fast. People are already talking about PCI Gen 6, Gen 7. That means more lanes, more SSDs. And a lot of that is riding on the coattails of the need for more memory bandwidth in AI, stacking a ton of GPUs or other chips that use PCI. And I think that we're going to get a bit of a free ride on that. Just as the hardware gets better, there's a ton of incentive for it. So don't look at RAM, look at SSDs. There's one caveat with SSDs. You need to parallelize. Remember, throughput on SSDs is really good. Latency is high. 40 microseconds. We've modeled, right? I have like a Desmos calculator somewhere where I've kind of modeled that the max sequential throughput you can expect, at least in Nomt, if you just read a state item, do a little bit of computation, read another state item, do a little bit of computation, waiting 40 microseconds each time, is about 6,000 transactions per second. Still pretty good. Still probably good enough for most applications. But if you really want to take advantage of this, you need a parallel VM, which I think is honestly pretty close to, as close to a free lunch as anything is in software engineering. Because usually, even when you have to retry a transaction, the state that you're loading is already in RAM. Anyway, so if you want to use Nomt and get the most out of it, you need parallelism. But you can still get pretty good results just with sequential. And just rehashing that. Basically, you want to send big batches of operations and get their results out of order rather than like send an operation and then wait for it to complete and then send the next operation. It's just way faster. Let's get back to Nomt. So, architecture of Nomt. Nomt is actually 2 databases, not 1. We have, and they're optimized for the different access patterns. One is optimized for updating and proving. You've done all the transactions in a block. You want to update it as fast as possible. And one of them is optimized for fast reads. So we have Bitbox and Btree. Bitbox is what stores the Merkle pages, stores all of the Merkle tree nodes. We have Btree, which is a custom Btree. And the aim here is to serve all state reads that fit within a page in a single I/O. So if you need to load like a bunch of smart contract code, you're going to need to do more reads for that because they just don't fit in a single page. But small stuff like account balances, you will always get it in one round trip. It won't clog up the queue. Here's how we store our nodes in pages. Logically, it looks like the thing on the left. In practice, it's just a vector of bytes, and it's the thing on the right. The thing on the left shows how like each page stores what we would call a rootless binary tree of a certain depth. So it stores like the left child, the right child, and then a few layers down from that in a binary tree. And then each of those children has its own sub-page and the root of the binary Merkle tree is stored outside of that. And this is a format that's known as the Proto-Van M de Boas layout. The main benefit that you get here is that whenever you're, say, traversing to a particular path down this tree, you always get all the neighbors. And you get 6 levels of neighbors at a time. So you do 1 I/O for every 2 to the 6 items in your database. So if you have every 6th power of 2, so if you have 2 to the 24, that's 16 million, then you need to do like 4 I/Os. If you have 2 to the 30, that's 1 billion, you need to do 5 I/Os. We keep the top level in cache. So up to 1 billion, you're just doing a single state, a single read from the database. We have B-tree, right? So this is our key value store, just maps, say, addresses to balances and you know, state item locations to state values. It's a customized B tree that's meant to be super space efficient so that we can keep the entire index in memory. We estimate, you know, and this depends on how long your keys are and how big your values are, but we estimate around 200 megabytes of memory for 1 billion items, so it's, or per billion items, so it's not that much. We keep a high-level in-memory index that's not stored on disk, that indexes into B-tree branch nodes, which are both stored in RAM and on disk. And we have B-tree leaf nodes, which only exist on disk, and large value overflow pages. We support values up to the gigabytes range, should you need that for some reason. Some engineering decisions. So we target Linux as first class. That's because Linux has some asynchronous I/O facilities known as IOU ring that are really good for maxing out the throughput of an SSD. We also target generic Unix and Mac OS because people use those things for development, right? Like people need to run a development node on their MacBook. We don't want all of the developers using Nomt to have to install Linux. We use what's known as direct I/O to maximize IOPS. That means that we don't use the operating system's own caching because it causes a lot of interference. We have our own caches. It's a single state database, so it only stores one finalized state. Any changes to that state must be in memory. So if your blockchain takes, say, a minute to finalize, your nodes are going to have to keep a minute worth of changes in memory. There are some engineering decisions that surround this. It kind of creates a bias for maybe using algorithms that you know, do single slot finality. But I think, you know, with the right back-off mechanisms, it could easily integrate with like the babe and grandpa of Substrate and Polkadot. And you know, that's also an engineering decision that is becoming very common over the industry. So for example, Geth also has a single state database. There are also some facilities for rolling back in case you need to revert finality and stuff like that. But Geth and Reth and Aragon and so on tend to just keep these single states unless they're running in a so-called archive mode. And it's written in Rust. Space usage, how much space does this use on disk? We estimate that 1 billion items is going to take around 150 gigabytes on disk. Again, depends on how big your values are. You have these large occasional jumps in space usage because of our page layout. Every time the number of items increases by 64. We're working to make this as gradual as possible so that your disk should fill up slowly and not like all at once just from doubling the size. That's something that we're going to aim for in V1 or shortly thereafter. And we're aiming to support tens of billions of items per every 4 terabytes of storage. So one 4 terabyte SSD should be enough to accommodate at least a few 100 million users. Here's an example of like how we can analyze the theoretical performance. If you assume there are 10 billion accounts, and you're doing just these simple transfer transactions with 2 random read writes, you have to do 3 reads and 5 writes for each account in that transaction, so the sender and the receiver. So you get 8 multiplied by 2, 16 IOs per transaction. If you take 1 million IOPS, assuming, you know, our engineering is perfect and we can actually max out the drive at all times, and no, we can't. There are some overheads. But assuming you can max out the drive at 1 million IOPS, you would be able to do 62,000 transactions per second at 10 billion accounts in the state. At 500,000 IOPS, so that's assuming like there are some serious overheads in our code, you could do 31,500 transactions per second. So we use this kind of arithmetic to guide where we think performance should be. We've set a fairly modest target for performance in V1, which we're aiming to release at the end of year. We're doing kind of our final milestone right now of testing, optimization, reliability, documentation. Expected end of year 2024 is to do 25,000 transactions per second with 1 billion accounts. Our current benchmarks on 128 million accounts are showing at around 40,000 transactions per second. Side note, this is assuming worst case random access, right? But most blockchain workloads are probably more like power law distributed, where 80% of the transactions use 20% of the state, or like maybe even more than that. Maybe it's like 90% of the transactions use 1% of the state. So some user level caching gets these numbers up quite a lot. However, you do have to account for caching in your gas cost mechanisms. Talk a bit about node requirements, like what we roughly expect. The RAM and disk size needed scale with the DB size. I think 4 gigabytes of RAM and 256 gigabytes of SSD for 1 billion items should be plenty. You need a disk that can do 500,000 IOPS consistently. If you're getting that from a cloud server, make sure you get those guaranteed IOPS. And CPU, probably need 8 cores. Pushing these IOs through the kernel is actually really expensive, and there's a lot of hashing and other stuff that we do. You might not need 8 cores, but it's good to have a little bit of a budget. You're probably not going to get the maximum throughput out of 4 cores. That's about it. I have a couple minutes. I have some appendices. Or I could take questions. Let's roll with questions first, and if there aren't questions, then we'll do appendices.
Okay, we got a question right here.
Do you think this database is suitable for Jam?
No, so Jam is, if you're talking about the main Jam chain, I believe that they have their own custom state tree, which is intended to be entirely in RAM. However, I think that this database is going to be really important for any kind of services that are built on top of Jam that need to scale to hundreds of millions or billions of users.
Awesome. Who else? That was everybody's question? Oh, here we go.
Yeah, I saw in one image with the distracted boyfriend one that you had like RAID 0. Like, so is the price of the node that you had there, is that with one disk, or is it like a RAID 0 setup?
Yeah, that's a good question. So a little bit of context for the audience. RAID 0 is where you have multiple SSDs all working together. So I threw that in as a little bit of an Easter egg. Like, none of the numbers or anything that I'm putting in this talk relate to RAID 0 or having multiple disks directly. We're talking about one large disk. However, there's a future scaling option that looks very good, which is to have multiple disks. Because if you have one disk at 1 million IOPS, then if you have 2 disks, you could get 2 million IOPS, right? Like double performance. There are some catches there, right? Like, how do you distribute the data across these disks? Future direction, but a very promising one.
Thank you.
Thank you. Anybody else with a question for Rob? Yeah, whip it. Damn, nice.
Hey, I'm curious about like extreme situation, like assume we have some airdrop. Okay. Is it better? Yeah. So we have airdrop, so we have to like transfer users a bunch of tokens, like for million users, for example. So we have to iterate over a large number of accounts. And I assume Nomt has the size of the keys are limited. So in case of Substrate, where the keys I assume unlimited, so we could just, well, if their keys are very large, we just go through. And in case of Nomt, if the keys that correspond to these users, they are larger than the limit, how do we handle this case? Is it even a problem at all? Because we, as you said, we kind of have worst case scenario which still works pretty fast, or you optimize for that case as well when we need to iterate over accounts.
Yeah, so we viewed iteration as like not the main goal, but it's certainly something that we support very easily due to our use of a B-tree data structure. And we should be able to do it at the speed of the drive. You know, for example, you just do a sweep left to right of all the branch nodes and fetch all of the leaves, you know, as fast as possible within them. So that was one question I believe that we should support, although we do not currently have an API for it. We should support ordered iteration very well. And the other question about handling very large keys, we use, and very large values, we use a technique that's common to B-trees, which is the notion of overflow pages. So if you have a very large value, we just stuff that into a couple extra pages and then hold a reference to them in the main B-tree. So we should support those as well, but again, it's not been a focus for V1.
Beautiful. Anybody else with a question for Rob? All right, we got one over here. Why don't you take this?
Yeah, sorry, I'm not so familiar with the matter, so maybe it's obvious, but why is it called Nomt, like with nearly optimal? Like, what would make it optimal, and are you planning to do that?
I guess nothing's ever perfect. So we're going to leave it at nearly optimal for now. Maybe at some point we'll do enough work that we believe it will be optimal. I mean, there are a couple algorithmic changes that I would be interested in pursuing. Like, I'm not sure that a binary Merkle trie is actually the best thing. There may be other data structures that let you pack the data even better and improve your access patterns even more. But it's certainly nearly optimal.
Thank you. Anybody else? Yeah.
Stupid question. Like, how is this something like will not be used in like in substrate terms, like the node, and chains will be able to use this instead of the what is it, the source DB or the parity DB? Like, how? Let's say, how can a chain developer like start to use this?
Yeah, I mean, this is something that you build a blockchain node around. I'd say it's the most critical blockchain node component for scalability. But you know, blockchain node has lots of things, like it has a VM, it has networking, synchronization, RPCs, all of that stuff. This is something for people deep in the stack that would then bring benefits all the way up the stack.
So it will be like, like it could be integrated in substrate. Like, I'm just like trying to translate it to something that.
Yeah. I mean, it could be like, you know, as far as I'm aware, there are no concrete plans to do that in substrate. However, I know many people are very interested in it, and it is something that could fit in with substrate.
Thanks very much. Anybody else with a question? Oh, come on, let's go.
Hey, I'm curious, what is the North Star for Nomt? I.e., do you think that it will replace RocksDB levels where everyone is in pain, especially when there's too much data? Or it's more for, you know, substrate ecosystems? Yeah.
Yeah. Sorry, could you repeat the first part of your question?
What is the North Star?
The North Star.
Yeah.
Yeah, it's to drive performance across the blockchain industry. I'd say it's very ecosystem neutral as where it sits in the stack. For example, like Sovereign SDK is going to be building upon it. I think that the benefits are going to be very large to the point where blockchain SDKs will kind of really want to integrate it. And we're in talks with like a few node developers about doing that. But the North Star is just build a really good database. Here's a component we could isolate. It's the main headwind on performance in blockchains in general. Let's solve that problem.
Nice, because switching is painful.
Very good. Oh, got a question up here. Jinwen.
Hi, Rob. We are bringing Merkle tree to Solana by utilizing Spark's Merkle tree SMT. So can we use Nomt for the data storage? For the data storage?
Yes, potentially, if you integrate it into your stack directly. So the tree that we support, in fact, is a kind of sparse Merkle tree.
Oh.
Yeah.
Yeah, exactly.
Great. One more? Rob, you've been so kind to answer these great questions. And thank you so much for coming on stage and telling us about this super exciting initiative.
Thank you, everyone.
Thank you.